Thank you very much. Thank the This work mainly done in Trinity, and some of it this is some of the explosion progenitor and explosion scenarios that we believe they are the progenitors of the 1A. Remember, when we talk about progenitor scenarios, it's also about the actual explosion itself or the binary configuration. And generally, I will put this here. I don't know how many will agree, but it doesn't matter. Generally, we have the double degenerate and the single degenerate, some double detonation substandard scenarios, and of course, other variations. But I want to point here that this is what a theorist would call as a diversity in the thermonuclear explosions. We are observers, and in the observing space, things look like this. This is a very nice plot originally from Taubenberger in 2017, and it shows the absolute magnitude in the y-axis and the decline rate, the decline rate in V-band, so the evolution of the light year. And all of the objects that they are used in cosmology are the ones in gray crosses. The black line is the Phillips relation. We also use 91T-like in cosmology, but there are, as you can see, color-coded here in this parameter space, other peculiar events, which we were certain that these have thermonuclear origin, but as you can see, some of them are bright, they are slower, brighter than what you expect based on their decline rate, etc.
Well done. Okay.
I think we're back. Sorry about this. So, as I was saying, the ZTF is an untargeted survey that covers the whole northern sky. Madeline already showed you the Palomar Observatory with the basically the telescopes that are used. ZTF, I have a nice video here that shows that in ZTF is finding a lot of supernova. And we started at March 2018. There are 3 filters. Mainly it's GNR, and there is some I-band observations there. There is deep limits, and we are spectroscopically complete for normal 1As up to redshift 0.06. So specifically, the data that we'll show is what Madeline showed. This is the DR2, this is the data release, the second data release for the ZTF for the 1A objects. These are in total 3,628 1As of all flavors. Remember, Madeline used basically subsample less than 0.06 and the cosmologically useful. This is supernova discovered from 18 till December 2020. ZTF is continuing through the next years, and there will be more data coming, obviously. And the important thing is that every supernova has at least one spectrum. And of course, some of them have more due to spectroscopic follow-up and etc. All the data, so the photometry, the classifications, the redshifts, light year feed parameter spectrum, and the host galaxy will be available, I think, the next month. But already, our collaboration have wrote some papers. There is how to say, a AAA special issue with papers from our collaboration that look at cosmology, they look at physics, they look at everything. And I definitely suggest every one of you to look at them. So for my job, one of the jobs, the first step is how to classify 3,600 supernova 1A. It's not easy. Basically, we developed a typing app, a website, we call it Typing App, where members of our collaboration, in total 32 users, provided sub-classifications of transients. On the left, you see a screenshot of what it looked like. So basically, everyone was looking something like this. We provided minimum information so that we will not bias when we want to say this is a 91T or a 91BG or whatever. Just basically, the information comes from the spectra. And then there was also some automatic approach. And then we did a dedicated effort for the supernova less than 0.06 to have the best classifications and subtypes that we can for the volume limited sample. For this 10% of supernova, they are still 1As, but we didn't subtype them. And another thing that I always say is that we learn a lot during this 1 year that took this project, how semi-automatic classification works. It's not easy, but there are ways to do better, and we hope we'll apply to large-scale servers in the future. So basically, we considered all the standard peculiar events, and this is just a plot of some of our objects alongside some matches and some comparisons with what a normal 1A is. We introduce a new subtype. Remember, this subtyping is basically what the spectrum looks like. It doesn't need to be physically something different for now. And I'm talking about the 18BYG-like, which is the yellow spectrum, as you see there. And eventually, after a lot of hard work, we managed to have a secure subtyping to map the thermonuclear supernova family. Then we did some light year fits. There is also uncertainties in the lines, but you cannot see them. I'm sorry about that. But basically, we used something similar what Thomas was doing with Gaussian fit properties. There is no underlying model. The only underlying assumption is the K corrections that we wanted to introduce. And this is basically based on the subtype of each one. And I list how we did it there. And then this is Gaussian process fit. The fit is happening both in time and in wavelength so that we can take all the information that we can. And then basically with the Gaussian process fit, you can get any parameter that you want. You can get peak magnitude, you can get some decline rate, colors, differences in the maxima of the two filters and whatever you want. In the paper, and eventually we'll provide all the parameters, even if we don't K-correct, if we correct with salt everything, just to have something consistent, and then with the template K-corrections for the subtypes, for the specific subtypes that we used. And on top of that, of course, we have the additional metadata, which is the normal salt fits, X1, C, and also the host galaxy parameters, which you will see when all the data will become available the next month. So this is the equivalent plot of the plot that I showed you before for Taubenberger. This is now the absolute magnitude in Z band and the decline rate in Z band for the 15 days. And as you can see, it looks more messy as the previous one. This is what I called the previous one a little bit ideal. There are many reasons why it looked like this, but generally, we recovered the parameters of the population, the thermonuclear diversity, in the photometric diversity that we see in we saw before. The next thing that you can do with this is, remember I was talking about the 10% that we don't have a clear subtype. For example, here is an approach that was inspired by the work of Chris Hassel in the past. So here you see, if we focus on the left, there is the time difference of the maximum between the I and G band. And on the y-axis, you see the color at 15 days, the G-I color. And as you can see here, the different subtypes generally have different spaces in this parameter space, with the exception of the 91T, and I will come back later to that. Now, as I said, I band was not well, didn't have the same amount of data as the GNR. So if you do the same exercise for GNR, this on the right-hand side, it gets a little bit more messier. And here the white points, as you can see, is the ones that we don't have a sub. So from this plot, we can more or less statistically have an idea what kind of subtypes are these supernova. Another thing that you can do is you can look at the hosts. Again, there are some points missing, and I'm really sorry about this, but I will explain. So on the bottom left, you see the host galaxies for the normal 1As. This is color on the left, which roughly tracks the star formation history, roughly. And on the x-axis is the mass. And I think you will believe me when I tell you that they are not there, but all the 91 PGs lie on the top mass panel here, and the 91Ts are basically the same as the normal 1As. And then all the other peculiar subtypes are shown here. I want to mention, maybe Subhan will talk also about this, that the host galaxies of the O3FG and O2ES appear to be different, and it is what we expect. The Superchandra are basically a little bit on the lower side of the mass and a little bit bluer, while the O2ES are basically the same as the 91BG, which lie here. There are exceptions, so these are very peculiar O2ES, like there is a paper in the literature. And another thing I want to mention is this is the host galaxies of the 1ACSM, which they seem to have the less diverse, they have the less diversity. All of them sit around 10 to the 10, with one notable exception. This is the only one ACSM that shows helium, the spectra. So this is a type 1A with helium interaction, and it is in a low mass galaxy. Now, since we have all of that, we have the subtype, we have the light curve, we have a spectroscopically complete sample. We can estimate now the relative rates. This was done with some simple simulations to recover the efficiency of each of the supernova. And this is our results. Remember, this is not absolute rates. This is observed fractions, basically. And from what you can see, 75% of the supernova that you will see are normal. Another 12% is 91T light. So the cosmology sample basically is 8 in the literature, so we knew that, and then we were able to put some rough estimates on the other subtypes. The difference here now is that we tend to find more 91T like than other surveys. There is some discussion in the paper. I don't have a lot of time to talk about this. But since I'm very close to the end, I think I will stop with this nice pie chart, which I think looks nice. And I will wait for your question. Thank you very much.